Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 3. Continuity on intervals and algebraic functions. Part 1. Okay, we have one last piece of terminology to learn that has to do with continuity of functions. And I know we've learned a lot of vocabulary today, but I promise this is the last vocabulary we're going to learn. The rest of this particular section is devoted to looking at specific types of functions, things like polynomials and rational functions, root functions, trig functions, exponential functions, and the inverses of all of those, and finding out kind of where those types of functions are or are not continuous. Okay, so last definitions are on this page. We say that f is continuous on an open interval. So remember, so far we've talked about whether f is continuous at a particular point, like at x equal a. Now we're going to be talking about being continuous on a whole interval of values from a up to b, if it's continuous at each x within that interval. Remember, this is the interval notation that really means the interval of x values where x is less than b but greater than a. So in this context, this is not an ordered pair on a graph, rather it is the interval notation that means exactly the same thing as a is less than x is less than b. So we're going to say that f is continuous on this interval if it's continuous at each of the points in between a and b. And here I've drawn a picture of a typical function that is continuous at all the points between a and b. It's also continuous the way I've drawn it for some points to the right of b and to the left of a. But we could go ahead and say this function, y equal f of x, is continuous on the interval from a to b, because if I choose any particular x value that's within this interval, that's in the interval from a up to b, you notice that the function is definitely continuous at that x value. I can draw the graph right through that point corresponding to x without lifting my pen off the paper. The function does not necessarily have to be continuous at the endpoint values, and here you can see that it is not. This function is not continuous at a, it is not continuous at b, but it would be continuous for any x value that I choose in between a and b, and in that case we say it's continuous on the open interval from a to b, and we use rounded parentheses to exclude those endpoint values, since we're not saying it's continuous at a or at b, just in between there. We say that f is continuous on a closed interval, and you notice here I've used the square brackets, which means that I'm going to be including the endpoints, and this is the same as this is the interval notation for the interval of values a is less than or equal to x is less than or equal to b, where we're including the endpoints. If the following is true, f is continuous on a closed interval from a to b if it's continuous on the open interval. In other words, just as before, if it's continuous at every x you might choose between a and b, and we have these endpoint values included on this little chunk of graph between a and b. So we're going to say it's continuous on the open interval if it's simply continuous from a up to b, may be discontinuous at a and b. We are going to say that it's continuous on the closed interval if these endpoints are included at each end of this chunk of graph in between a and b. Well, remember that if the endpoints are included, even though my function f is not continuous at a and is not continuous at b, it does mean there's some kind of one-sided continuity that's going on. Let's see if we can fill in these green blanks. So we're going to say it's continuous on the closed interval from a to b if first of all it's continuous at each x in between a and b on the open interval from a to b, and I can see this one is, there are no breaks or jumps or holes or anything like that between a and b, and if these endpoints are included. Well, what does that mean technically, that the endpoints are included? That would mean that f is continuous from the blank at a. Well, for this endpoint to be included, let's sort of block out the rest of the picture. Notice that the endpoint on the right chunk of graph, the chunk of graph that is to the right of A, is included, and that means that f will be continuous from the right as we come in this direction from the right, on the right side of A. So to be continuous on the closed interval from A to B, f will have to be continuous from the right at A. And what about at B? We want to also include this endpoint, sort of ignore the rest of the graph for a moment and just concentrate on B, and notice that this endpoint is included on the chunk of graph that is to the left of B. So I'm going to say, and from the left at B. And of course each of these things could be written out, what we mean by those. For f to be continuous from the right at A, remember that means that the limit as x approaches A from the right has to equal the value of the function at A, and that would be true if this endpoint is included. In a similar way, for f to be continuous from the left at B, it means that as we approach B from its left-hand side, the limit from the left of f as x approaches B from the left would have to be the same as the value if we plug b into the function. Usually we don't worry so much about the technical definition here of continuity on a closed interval. Usually we use it in a graphical sense, and we just look at this function and we say, it's continuous on the closed interval from A to B, because not only is it continuous in between, for each x in between A and B, but these solid dots appear at the end of my graph, as opposed to this graph where I have an open hole at the end of the chunk of graph that is between A and B. So this one is continuous on the open interval from A to B, but this picture would be continuous on the closed interval from A to B. Note again, though, that it doesn't mean that f is continuous at A or at B, only that it's continuous from the right at A and continuous from the left at B. Okay, let's go ahead and look at the last graph that I have down here and try to write down the interval on which this function f of x is continuous. This one's a little weird because I have a solid dot on one side of this chunk of graph that goes between A and B, but I have an open circle on the other side. And how do you think we might write down the interval on which this function is continuous? Well, it's continuous from the right at A, because I have this open circle here, but not from the left at B. So we just go ahead and say, well, I'm going to include the left-hand endpoint because the left-hand dot is included on this chunk of graph. And this function would be continuous on an interval that has the left endpoint included. But what about the right endpoint? That point is not included on this chunk of graph. The function is not continuous from the right, from the left, at B. And so we put an open parentheses there to exclude that right-hand endpoint. This is not an open interval or a closed interval. It's actually what's referred to as a half open interval. I suppose you could call it a half closed interval as well, but we like to stay on the optimistic side, and so we call it always a half open interval. Notice this function is also continuous in other parts, to the right of B and to the left of A, but we're just concentrating on how to express its continuity between A and B and whether to include the endpoint or not. And it's as simple as looking at whether the point at the end of that chunk of graph is or is not included on the graph. Well, let's try another example just so that you can get used to this idea of continuity on an interval. And here's an example at the top of the page where we have some crazy graph. It's all one graph, y equal f of x, and we are asked to determine the intervals on which f is continuous. Let's do one of the intervals together, and then I'm going to have you stop the video and try to do the others on your own. So remember that when we put an arrow on the graph, we mean that it continues in more or less the same way. So when I put an arrow here, it means that the function doesn't just stop. Its domain is not limited here, but it continues in this direction as x goes backwards towards negative infinity. By the same token, if I look at the x values over here on the right, since I have an arrow on my graph, we are assuming that this graph continues in this direction forever as x goes out towards positive infinity. So I can see there are certain discontinuities in this graph at 10, at 20, and so on. If I look at what's happening up until I get to this first discontinuity at 10, it looks like it's a jump discontinuity. That would be an interval of values on which my function is continuous. If the function continues and nothing else weird happens, and we will assume that nothing else weird happens, if it did, we would have to draw that portion of the graph. So I want to say somehow that this function is continuous for x values starting at negative infinity and going all the way up to this first discontinuity at 10. So how do I write that? I'm going to be starting at an x value of negative infinity, which remember really means we're going forever in the negative x direction. And I'm going to go all the way up until I hit my discontinuity at 10. That's an interval of x values, and we're saying that our function is continuous at each of those x values. If I pick any of them, my function is supposed to be continuous. I'm not supposed to have a break at that x value in my graph. Well, now we have to think about, for interval notation, what kind of parentheses we're going to use next to the negative infinity and next to the 10. Well, next to either an infinity or a negative infinity, remember we always use a rounded bracket. And that's because negative infinity is not a specific finite number that we reach. Rather, it's a concept. It's the idea that the x's go off in this direction forever and ever. So we use a rounded parentheses to indicate that negative infinity is not a number that we get to and stop at. Now for the 10, as we come in on this chunk of the graph, notice there is an open circle here at the end of that chunk of graph. This function would not be continuous from the right at 10. So that means that I need to put a rounded parentheses here. If this had been a solid dot, I would have put a square bracket because my function would be continuous from the left at 10. But because of the open circle, it is not continuous from left at 10, and so I have to use a rounded parentheses. So that takes care of this interval of continuity. And now what you want to do is look at the next interval from 10 to 20 and try to correctly write down the interval of continuity there with the correct type of parentheses at each of the endpoint values. And then do the same for all the other intervals on which this function, y equal f of x, is continuous. So stop the video, take a moment and do that, and then we'll go through it together. Okay, so for this interval, I can see that my function is continuous everywhere between 10 and 20. So that's going to constitute my next interval of continuity. But I just have to decide what kind of parentheses to use. When I look at this chunk of graph, there's an open circle at 10, so I need a rounded parentheses there. However, it does include its endpoint on the right side. This would be a function that is continuous from the left at 20, and so I want to put a square bracket next to the 20. this would be a half open interval. This, by the way, is an open interval. It's really an infinite interval, or sometimes it's referred to as a half infinite interval, but we would call it an open infinite interval. So now I have two of the intervals on which my function y equal f of x is continuous. Let's look at the next one. I can see the function also has a break at 30. So here's another interval. Between 20 and 30, there are no breaks. I can draw the graph without lifting my pen off of the paper. So at every point between 20 and 30, we know that the function is continuous. Now we just have to decide about the endpoints. If we look at this chunk of graph, it does not contain the endpoint here. There's a hole in the graph, so I have to put a rounded parentheses next to the 20. And if I look at this chunk of the graph, well, it continues downwards forever. There's this vertical asymptote at x equal 30, and so it never reaches a point on that asymptote. So there is no endpoint here. This just keeps continuing down forever, and it never quite reaches 30. In fact, this function is undefined at 30. There's no point on the graph corresponding to x equal 30, and for that reason, I put a rounded parentheses here. So my function is continuous. Remember here, we're really talking about the x values. We're not thinking about the y values and what's happening to y. All we're saying is that every point, every x value between 20 and 30 corresponds to a piece of the graph that is continuous through that point. So notice here that these are the x values at which my function is continuous. We're not worrying about what's happening to the output values. Sometimes people get confused because this is going down towards negative infinity, but that's the y values. The intervals on which a function is continuous are the x values for which that function is continuous. Okay, the next discontinuity would be at 40. It looks like it's a jump discontinuity. So we have an infinite discontinuity at 30 and a jump discontinuity at 40. And so I can see that my graph is continuous for every x between 30 and 40. Just as we said here next to the 30, we needed a rounded parentheses for this interval. We also need a rounded parentheses because there was no endpoint on the left-hand side of this chunk of graph. And if I look at the right-hand side of this chunk of graph, I have a hole in the graph there, and so I have to use a rounded parentheses next to the 40 as well. Let's go from 40 up to the next discontinuity, which appears to be another jump discontinuity at 50. And so we're looking at this little chunk of graph. Although I have some sharp corners, I still can draw this whole chunk without lifting my pen off the paper. So my function is continuous at every x value in between between 40 and 50. And what's more, the left-hand end of this chunk of graph contains its endpoint, and the right-hand end of this chunk of graph contains its endpoint. So I get to put square brackets here. The function is continuous from the right at 40, and it is continuous from the left at 50. So we include those endpoints in our interval on which f is continuous. Okay, let's look at this last one. Remember, this continues off forever in this direction towards x is going towards positive infinity here. So the next interval that I'm looking at it being continuous on goes from 50 onwards forever. We're assuming there's no other weird holes or jumps in our graph, so it's going to go to positive infinity, which you can either write as infinity or plus infinity. If we look at this chunk of graph, there's an open hole here. The endpoint is not included, so I put a rounded parentheses. And remember that we never reach infinity, and we indicate that by always putting a rounded parentheses next to an infinity or a negative infinity. It's not a number I ever reach, so I would not want to use a square bracket there. Okay, well, that's great. We have learned all kinds of terms about continuity. We learned the intuitive definition of continuity, that you don't lift your pen off the paper. We learned the precise definition of continuity with the 3 conditions that we had to check. We learned about continuities that were removable or non-removable, and the non-removable discontinuities could be ones that are either jump discontinuities like here, or infinite discontinuities like we would have at 30. Then we learned about continuity from the left and from the right. It just depended on whether or not the endpoints were included on the chunk of graph that we were considering. And we discussed what we meant by being continuous on an open interval, on a closed interval, and actually, although we didn't write out the definition, we wrote down what we meant by it being continuous on a half open interval like this one, or on an infinite interval like this one. Well, that's great, but in practice, we are usually given certain types of functions. There are a lot of them that we work with often: polynomials, rational functions, root functions, trig functions, exponential functions, things like that. Those are the functions that we work with most often, and we would like to make some general statements about the continuity of those different types of functions. And what I would like us to do is to begin with an example. Suppose I ask you this just very general question: where is f of x equal x cubed minus 6x plus 4 continuous? Instead of saying, is it continuous at x equal 5, for example, and having you figure that answer out, I'm saying, where is it continuous? So I'm asking you to consider the entire real number line and decide at each of those x values that you might think of from minus infinity to positive infinity, is f of x continuous? So here's a little question. How do we answer this? Do we check the 3 conditions in our precise definition of continuity at every real number? I mean, do I pick x equal 5 and check whether or not it's continuous there, and then check x equal 5,000 and check whether it's continuous or not there? But there are an infinite number of real numbers. If you did it that way, you would be doing this problem for the rest of your life, and you wouldn't even have scratched the surface of answering the question. So that wouldn't be a good way to do it. So I'm going to put no. We don't want to check the 3 conditions for every real number. But to help us answer this question, let's just try a real number and decide whether or not this function is continuous at that real number. So we're just going to check one number, and I think once we do that, you'll see how to do it for all possible numbers. And I just said, let's consider x equal 2. I pulled that out of a hat. We could have done x equal 10 billion, and that would have worked just as well. Well, if we just considered whether or not it's continuous at 2, we would check the 3 conditions in our precise definition of continuity at the value x equal 2. Remember, the first condition was, is f of 2 defined? Well, if I plug 2 into this function, I cube it, I do minus 6 times 2 plus 4, yeah, that's going to be defined, right? In fact, no matter what real number I plug into this, it looks like I'm going to get some real number out. It's not undefined anywhere. So yes, it is defined. And if I wanted to figure out what f of 2 is, I would just plug in 2 cubed minus 6 times 2 plus 4. Let's see, what does that give me? That's 8. Minus 12 is negative 4 plus 4, that's 0. So it happens to give me an output value of 0. Well, let's go to condition 2. It satisfies condition 1. Let's see if it satisfies condition 2. I want to ask, does the limit as x approaches 2 of f of x exist? Well, let's see. That means that I'm trying to find the limit as x approaches 2 of my function f of x. Well, what is f of x? It's given by this formula, x cubed minus 6x plus 4. So I'm finding that limit. Is that a limit we know how to do? Well, yeah, it is, because what kind of function is this? This particular function is a polynomial. And because it's a polynomial, what do we get to do to figure out the limit? All we have to do is direct substitution. So yeah, the limit exists, and I can certainly find out what it is by just replacing all the x's I see with a 2. So I would do 2 cubed minus 6 times 2 plus 4, and hey, that's exactly the calculation I did up here So that gives me 0 as an output value. All right, so the limit does exist, and because it's a polynomial, we get to evaluate it by just plugging the value that x is getting close to, namely 2, right in place of x. Okay, so it satisfies condition 2 in our definition of continuity. Well, let's check condition 3. Is the limit as x approaches 2 of f of x the same thing as f of 2? Well, yeah. I mean, f of 2, how did we find that? We found that by plugging 2 in, and we got the value 0. And the limit as x approaches 2 of f of x, well, because it was a polynomial, how did we find that? Again, we did it using the same calculation we did to find the value of the function, because we got to use direct substitution. So the way that you find the limit of a polynomial is precisely the same as plugging the number into the polynomial. So of course these two things are going to be equal to each other, because that's precisely the way we find the limit of a function if it happens to be a polynomial, is to plug that number right into the polynomial. So yeah, of course those two are the same. So yes, this function is continuous at x equal 2. It satisfies condition 1, it satisfies condition 2, and it satisfies condition 3. Mainly it satisfies condition 3 because that's how you find the limit of f of x if it happens to be a polynomial. All we do is we actually plug 2 into the function, so of course it's going to equal f of 2. Okay, well, what have we figured out? We figured out that this function is continuous at one real number, namely 2. We were asked to decide where is it continuous, so what other real numbers would it be continuous at? Well, let's answer this question down at the bottom. Would this be true at other x values? In other words, would we find out that it is continuous if I'd chosen something other than 2? Suppose I'd asked you to check whether this is continuous at x equal 5. Well, yes, it would be continuous because you go through exactly the same steps, and to find the limit as x approaches 5 of this function, it's still a polynomial. So how would you do that? You would actually plug 5 into the function, and so of course those two things would end up being equal to each other. The limit would exist, the function would be defined at 5, and the two answers that you get would have to be the same. So yeah, it would be true at x equal 5, say. Would it be true at x equal 5,000? Sure, you'd go through exactly the same process, and to find the limit as x approaches 5,000 of f of x, you would plug 5,000 into the function, so of course you'd get the same value as if you find f of 5,000. So at each a value between minus infinity and infinity, this function would be continuous at that a value. In other words, this function, which happens to be a polynomial, is continuous at every real number from minus infinity to infinity, because you could go through this same process at every real number. So the answer to our question, I'll just put down here on the side, answer is that f is continuous every real number. In other words, it's continuous on the interval of x values stretching from minus infinity all the way to positive infinity. Or alternatively, you could just say f is continuous at every real number. Or another way that we often say it is that f is everywhere continuous, meaning it's continuous at every real number. Okay, let's go ahead and see if we can do a sort of generalization of what we have just said. And try to say something about polynomials in general rather than just that specific polynomial that we just looked at. So recall from the earlier section that we talked about, where we were talking about computing limits, we said, it was really the last section in this series of videos, we said that if p of x is a polynomial, then we have a special way of finding the limit as x approaches a of p of x. We said that if it's a polynomial, we are allowed to use direct substitution. And so to find the limit as x approaches a of p of x, what do? We just take whatever the rule is for p of x, and everywhere we see an x, we just replace it with a. We use direct substitution. Well, implied in this statement that I've just written down are actually three things. One thing that's implied is that P of A is defined. And of course that's true for polynomials. No matter what real number you plug in, you get some real number out of it. There are no numbers that end up giving you an expression that's undefined. So one thing that's implied in this little sentence that I have right here is that P of A is defined. Another thing that's implied in this little statement that we have is that the limit that's on the left-hand side exists, because we get to figure out what it is by just plugging A into our polynomial. So the second thing that's implied in this single statement is that the limit as x approaches A of P of x exists. And of course the third thing is that the two things are equal to each other. That's really just this statement. So the third thing is that the limit as x approaches A of P of x is exactly the same thing as P evaluated at A. Well, what does this mean? These are the three conditions in our careful definition of continuity at A. So this means f is continuous at x equal A, because this is precisely the definition of continuity at x equal A. So now we know that, well, I shouldn't say f, I should say p here, because we're using p for our polynomial. So p is continuous at x equal A. Well, would this be true for any A, any real number A that I chose from minus infinity to infinity? Yeah, sure, it's true. You can choose A equal to negative 100,000 if you want to. You can choose A equal to 200.135410. You can choose any value you want to for A from minus infinity to infinity, and these three statements would still hold true for that A value. So I'm going to put yes, it holds for any A from minus infinity to infinity. So if I ask you the question, on what interval is P continuous, you would say it's continuous for every real number, in other words, for anything from minus infinity to infinity. It's exactly the answer we had for our particular polynomial in the last example, but now we've shown that it's true for every polynomial that you could possibly conceive of. So here's our theorem. A polynomial is continuous, and I put blank here. And what word do you think might go into that first blank? Well, it's continuous, we could say, at every real number. Usually what we say is that, we sort of shorthand that, and we say it is continuous everywhere. Or sometimes you'll hear the words reversed, and you'll hear P is everywhere continuous. And that really just means that it's continuous everywhere. In other words, at every real number from minus infinity to positive infinity. Any real number that you can think of, your polynomial is continuous there. And I put down a little extra thing here just to emphasize what we said before. That is, it's continuous on the interval from minus infinity to infinity. Every possible real number. And another way to think about this, if you remember, a polynomial has a domain that's all real numbers. There are no denominators that could go to 0, no even roots of negative numbers in a polynomial. Any real number you plug in, you get some answer out that's defined. So a polynomial is continuous everywhere from minus infinity to infinity, and this interval, minus infinity to infinity, is also the domain of any polynomial. So another way to say this, I'll put i.e. It's continuous everywhere on its domain. On its domain. And keep that in mind. So polynomials are continuous everywhere they're defined, everywhere on their domain, which is all real numbers for a polynomial. Okay, the next thing I want us to look at is another class of functions. remember that if p of x and q of x are polynomials, then p of x over q of x is a rational function. So that's the next type of function for which we're going to discuss the continuity. Okay, if p of x and q of x are polynomials, then when we want to find the limit as x approaches a of p of x over q of x of that rational function, remember that we are allowed to use direct substitution just like a polynomial. So to find the limit, all I do is replace all the x's I see with an a. So I would have p of a over q of a, provided, remember with rational functions it's just a little more complicated, we had to say provided the denominator doesn't turn out to be 0. So provided q of a, the thing that's in the denominator here, is not equal to 0. If it is equal to 0, then that's going to be a place where the limit does not exist, because q of a would be 0 and we would end up with an expression that is undefined. So, okay, what does that mean? When we ask where is p of x over q of x continuous, well, look at the statement that we have right here. This is really, again, our shortcut statement of continuity. Remember, we had the long 3 conditions like we wrote out up here, and this was like the shortcut statement for a function being continuous at a particular point A. That's exactly what we have here. Inherent in this one statement, just like we discussed and sort of pulled apart into 3 conditions up here, we could do the same thing here by writing p of a over q of a, as long as we're at a place where q of a is not 0, where the denominator doesn't turn out to be 0, then p of a over q of a will be some number, so p of x over q of x is defined at a. Also, the limit as x approaches a of p of x over q of x exists as long as we're away from a place where the denominator ends up being 0 when you plug a in. And these two things are equal to each other. So this is really the definition of p of x over q of x, that function being continuous at a. And so when we ask where is p of x over q of x continuous, it will be continuous at every a value except where the denominator ends up being equal to 0. So we could say p of x over q of x is continuous everywhere except values of x where q of a, or we could say in general where the denominator equals 0, and at those values the function will be discontinuous, and that would be true just because when you try to plug those values in, you get a 0 in the denominator, your function isn't even defined at such a value, and so you would end up not satisfying condition 1 in the 3 conditions for continuity. Your function would not even be defined at that particular value. So maybe I should add right underneath here, p of x over q of x, that rational function, is continuous everywhere except where the denominator is 0, and at those a values, the values of a that you plug in and get 0 as an output, it is discontinuous. So I'll just put in parentheses here where it would be discontinuous. Okay. So let's kind of summarize that in a theorem. A rational function, meaning one polynomial p of x over another polynomial q of x, is continuous everywhere it is, and one way of saying it is everywhere it is defined, because that's the same as saying everywhere where the denominator is not equal to 0. So I'll say everywhere except where the denominator is equal to 0. Now, keep in mind that if you think about the domain of a rational function, that's actually the same set of numbers. A rational function is continuous everywhere except where the denominator is 0. And the domain of a rational function is all x's except the ones that make the denominator 0. So just like with a polynomial, remember we said a polynomial is continuous everywhere on its domain, we could actually make the same statement about a rational function. A rational function is continuous everywhere on its domain. So let me just add that. Not much room here, but let me just add that on here. I'll say i.e. everywhere on its domain. Or if you want to, you could say everywhere in its domain, same thing. So polynomials are continuous everywhere on the domain. That just happens to be the whole real number line. Rational functions are continuous everywhere on the domain. That's everywhere except where the denominator ends up being 0. Well, let's try a couple of examples, and I think it will help us to sort of solidify and understand exactly what those theorems are telling us. Let's look at the following example. Let's determine where this function, g of x, is equal to x squared plus 7x plus 10, all divided by x to the 5th minus 4 times x cubed. That looks kind of complicated. We're going to try to determine where that's continuous. And I want you to go ahead and think about what type of function this is, and then use that to help you decide where g of x is or is not continuous. And once you've thought about that one, I'd like you to think about this one, determine where this function, f of x, is continuous. And look at this function, it looks really nasty. 22x to the 100 minus 75x to the 40 plus 1. It'd certainly be difficult to figure out where it was continuous by trying every real number from minus infinity to infinity. But if you can determine what type of function that is, you can use what we said on the last page to help you decide where this function is or is not continuous. So take a moment and stop the video and work on these two examples, and then we'll go ahead and go through them together. Okay, let's look at the top example. Can you tell me what type of function this is? Well, if we look at the function in the top, x squared plus 7x plus 10, that is a polynomial. And if you look at the function in the bottom, x to the 5th minus 4x cubed, that is also a polynomial. If I have one polynomial divided by another polynomial, it means that g is a rational function. And we just got through saying that a rational function will be continuous everywhere except where the denominator is 0. So I'll put, so g is continuous except where the denominator is equal to 0. Well, that means we just need to look at this denominator and find the x values that would end up giving us a 0 in that expression. So what am I going to do? I'm going to ignore the top of this. We don't really care anything about the top where it's 0 or anything like that. What we are interested in is the denominator. We're looking for the values of x that would make that expression, x to the 5th minus 4x cubed, equal to 0. In order to determine where this is 0, it's probably easier to have it in factored form. And I notice that there's a common factor of x cubed in the denominator, so let me start by factoring that out. I would be left with an x squared minus a 4. And let's see, could that be factored further? It could, because x squared minus 4 is the difference of two squares, x squared minus 2 squared. So let me factor it completely, and that will give us an easy way to determine the values of x that would make that denominator 0. So I have x cubed for my common factor. Now I'm factoring what's left, the x squared minus 4, that would factor into an x plus 2 and an x minus 2. Now we should be able to look at this denominator and decide what values of x would end up making that denominator equal to 0. If you want to, you can take the whole denominator and set it equal to 0, or you can simply look at it and say, well, this denominator will be 0 when any of these three factors is equal to 0. When is x cubed equal to 0? Well, that would be true when x equals 0. 0 cubed is 0. When is x plus 2 equal to 0? Well, that would be true when x is equal to negative 2. And when is x minus 2 equal to 0? Well, that would be true when x is equal to a positive 2. So 0, negative 2, and 2 are the values that make the denominator of g of x equal to 0, and those are precisely the places where g is not going to be continuous. It'll be continuous everywhere except these three x values. And at those three x values, 0, negative 2, and 2, g will be discontinuous. G won't even be defined at those values, so that it would fail the first condition in our precise definition of continuity. So to answer this question, determine where g is continuous, there would be different ways of expressing our answer. One way would be to say that g is continuous for all real x except, in other words, x not equal to negative 2, 0, and 2. I just tried to put them in order. So g is continuous for all x not equal to negative 2, 0, or 2. Or if you wanted to, you could say g is continuous, and you could list the intervals on which g is continuous. Well, if it's not continuous at these three x values, and it is continuous everywhere else, then if you thought about the number line, you'd be saying that it's continuous from negative infinity up to negative 2, but not including negative 2, it's discontinuous there. And it is continuous from negative 2 up to 0, but not continuous at 0, so I would put a rounded parentheses there. It's continuous from 0 to 2, and again I put a rounded parentheses at 2 because I know it's discontinuous there, and then it's continuous from 2 to positive infinity. But that's a kind of a clumsy way to express the answer. It's continuous on these intervals, these four intervals. It's probably easier to just say g is continuous. You could write in here for all real x not equal to negative 2, 0, or 2. Or you could say g is discontinuous at negative 2, 0, and 2. Okay. I hope you had a chance to think about this other function, f of x. It looks sort of nasty because you have these big powers on the x, 22x to the 100 minus 75x to the 40 plus 1. But what type of function is this? Even though there are large exponents on there, this is a polynomial. And once you know what type of function it is, we already have a theorem concerning polynomials. And we said no matter what polynomial you are looking at, it is continuous everywhere. So this function f is continuous everywhere. Or sometimes we say it is everywhere continuous. Or another way of saying it is continuous on the whole real number line, meaning from minus infinity to positive infinity. So you could also say f is continuous from minus infinity to positive infinity.